Hi, Geometry. Welcome to 2.1, Inductive Reasoning. This is where we kind of start using a different frame of mind for when we do the geometric proofs. So those will be coming up. More of that later. Here we go. I can describe patterns using inductive reasoning and make conjectures, and I can use counter examples to disprove conjectures. All right, here we go. So we're going to be looking for patterns. And nothing really major here. So this is just an intro section. First of all, describe the pattern here. 3, 6, 9, 12, 18. I'm sure you can guess that the next one's going to be 21, 24, 27, etc. These are our multiples of 3. I like to assign multiples of 3 because it throws people off. How about this one? 1, 4, 9, 16, 25, etc. Well, to go from here to here, we have to add 3, add 5, add 7, add 9, etc. But take a look at another one. Basic, I'm going to write, you're going to add consecutive odd numbers. But another reason these are famous is because these are perfect squares. 1 times 1, 2 times 2, 3 times 3, 4 times 4, etc. So, be really familiar with these. It's going to pop up a lot, not only in geometry, but in Algebra 2 and pre-calculus, especially when you do sequences and series. This one's a very famous series or sequence. Aside from here, I can take these two, add them up, and get this one. Take these two, add them up, get this one. Take these two, add them up, and get this one. Take these two, add them up, and get this one. So basically, to find the next number, you have to take the sum of the two previous numbers. This is really famous. If you read any of those Dan Brown books, this was probably brought up. This is called Fibonacci sequence. I think that's how you spell it. Any case, so let's go to our key concept. Inductive reasoning, a conjecture. So this is kind of like your idea of what's happening. Your pattern is an unproven statement that is based on observations. So, I mean, this is unproven, but we could pretty much use them. You use inductive reasoning when you find a pattern in specific cases and you want to write a conjecture for a general case. Let's end that with a period. All right, so the first one is actually kind of easy, but you are expected to be able to draw figures. So draw the next pattern. And this one is famous also, Sierpinski. Remember that 3D Sierpinski triangle that we made? Well, here we go. So let's see here. Just going to make it bigger. Okay, now this has 1, 2, 3 sections. This had 1, 2, and this had 1. So we're going to make 4 sections. And I hope I don't mess this up. One, 2, 3, 4 on the bottom. Beautiful. Let's see. There we go. Okay, that wasn't too bad. This is kind of hard to draw. Good luck with that. Example 2. Describe the pattern in the numbers and make a conjecture. Well, notice that we're multiplying by 11. Now, I like to show students this right here, but the conjecture is, let's look at 53 multiplied by 11. So what you're going to do is put the 5 here, the 3 here, add them up. That's the number in the middle. And that's going to be true. But of course, if we look at this one, the 4 on the outside, the 8 on the outside, split them up. But when you add them up, it's going to carry 1 over. So that's why you get a 5 here. How about this one? This one's kind of neat. Find the following and make a conjecture. Okay, well, 8 times 1 is 8, plus 1 is 9. 12 times 8 is 96, plus 2 is 98. 123 times 8 plus 3 is 987. I know you're probably wondering how I did that, but I worked this out earlier. Take a while, guess what this one's going to be. 9876. It's pretty cool, isn't it? So follow that pattern. Make your conjecture. All right, the next page. Okay. Disproving conjectures. To show that a conjecture is true, you must show that it's true for all cases. So you can show that conjecture is false by simply finding one counterexample. Basically, an example that doesn't work. So basically, let's underline counterexample here. So counterexample, something that doesn't work. If you can find one counterexample, you're done. Okay. Find a counterexample to disprove the conjecture. Supplementary angles are always a linear pair. All right, so for instance, remember what supplementary angles are? Two angles that'll add up to equal 180 degrees. For instance, these two. These are supplementary angles. They make a linear pair. It forms a straight line. Well, here's my counterexample. I wonder if that's one word or two words. In any case, split them up. Put 30 here, 150 here. There. You have supplementary angles, but they don't have the same vertex, so it doesn't form a straight line. So we just proved that always is not the case. Here's the example, and I just thought that these were pretty interesting. 1 times 1 is equal to 1. 2 times 2 is 4, but you have 1 plus 2 plus 1. 3 times 3 is 9. 1 plus 2 plus 3 plus 2 plus 1. It's like a palindrome, is that right? 4 times 4, look at that, it's just kind of cool. And here's that example that I showed you earlier. Okay, so everybody have a really nice afternoon. Enjoy.